So one strategy in making these images where it comes back to a point is we have our object that gives light rays, and then it goes through some kind of shape which then changes it to going parallel. And then on the other side we have a similar shape which changes the parallel rays back into a single point. As it turns out that in order to achieve this surface here has to be a hyperbola. If you're interested in all the glory detail, you can look at the textbook by Height in chapter 5.2.1, and they'll deal with how you get the fact that it's a hyperbola or an ellipse depending on the relative index of refraction. However, hyperbolas and ellipses, they're really hard to make. The tolerance that we need for these surfaces in order for us to have fairly good optical quantity is we have plus or minus lambda over 4. At the very least, you can recognize that if you have bumps that are as big as lambda over 4, you're probably going to start getting interference. So we're talking about hundreds of nanometers here. Very, very small tolerance. We do have ways to make what's called aspherical lenses, non-spherical lenses nowadays, such as these hyperbolic shape, but they're not as common. As I've hinted by the word aspherical, the more common type of lenses are spherical, meaning we get portions of a sphere. So we take a big giant sphere and we take a small little chunk of it and we use this section as part of our lens, basically. Why the sphere is so much preferred is because as you take a curved surface and another curved surface and you rub them against each other, because as you move them along, let me try a different color here, only for a sphere that if you move them, they will still mate perfectly. For any other shape, they will not fit as well. There are points that fit better than others, but for every single point to fit, both of these surfaces must be spherical. So if you have two sort of curved surfaces and you rub them against each other with some polishing compounds and some abrasive material, eventually both of them will turn spherical. And that's why it's very easy to make these sections of spheres for our lenses. And so traditionally, spherical is definitely preferred. And so let's see what happens when light rays, or technically light emanating from a single point, interact with a section of a sphere. So there's a number of approximations that we do make in order for us to have an easier time analyzing this system. First thing, we're going to make the paraxial approximation. This approximation is so famous it gets its own name. Paraxial meaning close to the optical axis. Okay, what we mean by the optical axis is we mean that if we have a spherical surface whose center could be way back here, this line, this radius, we call the optical axis, because if we have an object over here, it's going to send out some light rays, and as long as these two things are symmetric, at the very least, we'll see how it works out even better than that. These two rays, because they hit the same point on the sphere, spherical symmetry, it comes into a point which eventually forms our image. Couple names, we will call this S, we'll call this P, and so we have to start analyzing these things. Being close to the optical axis means that these angles are all small. These angles are small, and that we can make a bunch of approximation as we always famously do. So let's start naming some of these variables. We call that L object, L image. Making the distinction here, this one is to H, where the light ray hits here, and this distance we call the object distance, goes to the tip of the lens. Slight distinction there. And then of course we have the center of the circle somewhere back here, I guess. That's the center of the circle, resulting in a certain radius. And then we can name all these other angles that we are very fond of. We have N1 and 2. So this is the outside medium, and then this is the lens in our case. This still has to follow Snell's law. So we know this is the transmitted angle, this is the incident angle, and then we can relate this angle, alpha, and that angle, beta. So what the approximation allows us to do, first of all, is we can say alpha is about 0, because as we say, these beams are very close to the optical axis. Same token, beta is about 0. On top of that, I guess we forgot to name this, we call this phi, angle of the arc angle, I guess, of the radius. So that's also equal to 0. You know how we love small angle approximation. And then we can also say that LO is about the same as SO, LI is about the same as SI, as we have seen on this diagram. This little bit of distance, once the rays get closer to the axis, it starts to vanish quite quickly. And so we can start deriving Snell's law and working with all these different angles to find out what the incident angle and the transmit angle tends to be. So using geometry, as geometrical optic implies, you use a lot of geometry. So theta I would have to be, let's see, this is going to be 90, and this angle here is phi. Sorry, this angle, this angle between the tangent to the circle and this drop down vertical is phi. So therefore that must be 9 degrees minus 9 degrees minus alpha minus phi. So it's alpha plus phi. Theta t is 90 minus beta minus 90 minus phi, using this triangle over here. Oops, this triangle over here. Which equals phi minus beta. Then dumping in Snell's law, we get N1 sine alpha plus phi is equal to N2 sine phi minus beta. And once again, small angle approximation, if both alpha and phi are small, then the sum of the angle is also small, and this one's even smaller. So sine of theta is equal to theta, so this is just that. Equals N2 phi minus beta. And then, once again, small angle approximation, we can say that the theta is roughly equal to tangent theta, which we can make into these various things, with also the added approximation of that L and S is basically the same. And then we cancel the h's out, and we get N1 SO plus N2 Si is equal to n2 minus n1 over r. R being, of course, the radius of the sphere that we're dealing with. Notice one thing though, this equation here no longer depends on h. It doesn't depend on phi or alpha or beta. All it depends on is the two medium and the distance between the image and the object. So what we're basically saying is, given a spherical surface, we have a point, which is our object. It will send all kinds of rays, and then they all get collected at the same point, which is great, which is exactly the image we're expecting. So under all these somewhat strong assumption of the rays are close to the optical axis, then we can use a sphere or a section of a sphere, which is easy to make these image points. Now, in applying this formula though, there's some sign convention you have to be careful about. So the way I drew it before, with the object like this, that's when everything is kind of positive. We got Si over here, and we got SO over here, and we call that a positive radius. So in this case, we would have radius is greater than 0, Si is greater than 0, So is greater than 0. Now, as counterexamples, we can also have R being negative. Not often thought about in that way, but if the radius, if the piece of glass was to be curved that way, then the radius is actually back here. And so in this case, we would call R to be negative. For this particular case, chances are you would also get the rays going like this, and so you have to extrapolate back to find out where the image actually is. And so in this case, the Si, which is this distance, is also negative because it's not where we expect. So is still going to be positive because you can't image backwards. Now, R and S is also independent. You can also have a case where you have a fairly shallow thing, but your image starts quite close, so it doesn't quite bend all the way, and so the image is actually back here. And in this case, R will be greater than 0 because it's curving the way we expect it to. Si will be negative because it's actually behind and outside the lens or the interface, and then SO is still going to be positive. So these sign conventions you have to be careful to think about when you apply this formula. Now, this is just half the story though, because we've successfully entered into the transparent media, the glass usually, but we haven't exited it. Usual is that it's curved on both sides, and we can use spherical sections on both sides, and we can analyze and see how that all plays out.